Okay, so let's start with our today's content, that is talking about the torque. Sorry about the distortion here. Okay, so basically we talked about the kinematics in the last lecture, that is basically the range of motion, and we talked how the range of motion that is produced in the human body is all based on the rotational motions. That's why we measure them in degrees. Similarly, the force that is used for producing that motion is called torque, and torque is nothing but a rotational force that you can see here. The unit of force is Newton, and the unit of torque is Newton meter. Torque is usually represented as F into R, where F is the raw force and R is your moment arm. Here in this diagram, you can see that we have elbow flexion presented here. We have an internal torque and we have an external torque. Both of them are equal and counterbalancing each other. That's why we see this elbow in a static position. Okay, so basically what is external torque? External torque is basically your EF, that is external force, and D1, that is your external moment arm that you can see here, and this brown line represents that. Similarly, you have an internal force, and D, that is your internal moment arm, that is represented by this. Moment arm is basically the distance between the axis of rotation. This is your axis of rotation and your line of action of the force. This is the line of action for the external force, and this is the line of action for the internal force. Now the question is, why the force vector of the external force is smaller as compared to the internal force? Pause this video for 30 seconds, think about this question and answer me, and then restart this. Okay, so the external force is smaller as compared to the internal force because internal force has a lower moment arm. Okay, the moment arm is smaller, but the external force has the higher moment arm. If the and torque is basically directly proportional to moment arm, and torque is directly proportional to force. If there is a greater moment arm, then you need less force to produce the same amount of torque. Okay, that is what is happening here. D is equals to RF. Okay, now have talked about torque. Here let's talk about the mechanical advantage. Mechanical advantage is a concept where you can produce greater torque with the same amount of force. Okay, or you get an advantage in producing torque with lower force. Okay, so you already have gotten about this idea now, that how you can increase the torque with smaller force, that is by increasing the moment arm. Okay, that's basically your mechanical advantage. In this example here, we will talk about anatomical pulleys. A pulley is a machine that helps you leverage your force, okay, or increase the moment arm of that force. Now in the body, we talk about these bones called sesamoid bones, and one of them is written here, that is your patella bone. Now for the first picture, let's assume that there is no patella here. If I darken this up, okay, let's assume there is no patella bone here. Then the moment arm produced in the knee joint to the line of action of the quadricep pull would be this one. However, if we assume that there is a patella there, which is there, and that's the function of patella, then we can see that the moment arm has increased. So basically, with the same amount of force, greater torque is produced here. That is because of the moment arm that has increased. So again, torque is equals to Fr. Torque is directly proportional to R as well. So torque increases as the moment arm increases. So that's the function of pulleys in the human body, which are usually sesamoid bones. And the sesamoid bones, one of the biggest sesamoid bones in the body, is your patella bone. Okay, now let's go to the next topic, and we discuss that in the continuation of our principles of human motion. Thank you.